bit about the SysNova scheme itself. It's a technology challenge scheme. So the idea is that we test many alternative solutions in parallel for future space missions. So the idea is to test various mission concepts at the same time and choose the one that is the most promising and continue on this concept through the pre-phase A study at the concurrent design facility at ESTEC.
The main goals of the mission would be to have enable low computing and enlarge the envelope of the mission in terms of eclipse and observation for large platform, but also to embed larger models on board a smaller platform, and also to prove that neuromorphic computing can be a suitable paradigm for Earth observation mission in synergy with RGB application. And this has been mapped in different objectives that mainly we want to see if neuromorphic sensing can complement classical vision. We want to show the neuromorphic edge computing can enable complex neural model in space, and demonstrate this technology across multiple domains at system level and application level.
So we have 4 main objectives. First, rapid wildfire detection. We want to move from the current hours-long ground processing pipeline to onboard detection in minutes. Second, integrated fire and air quality assessment, correlating optical fire detections with atmospheric data from Sentinel-4 and Sentinel-5. Third, we want information-centric downlink. Of course, instead of dumping raw imagery, we transmit semantic products, aiming for a 10 times data reduction. And fourth, a mission that fits, of course, within the 50 million euros cap. So below you can see our success criteria. The key one is latency. P95 under 10 minutes from acquisition to user alert. That is the number that drives most of our architectural choices.
The main motivation, as we all agree today, is that future Earth observation missions will need to react faster and handle more data directly on board. And as the previous teams mentioned, in current concepts, the spacecraft still collects large amount of data, downlink, and then the main interpretation happens on ground. The idea of NeuroRespond is to move part of this first decision layer, let's say, on board, where event-based sensors can detect changes rather than continuously producing full frames. And also using neuromorphic processors, we can classify or filter very relevant activity at low power. So I would like to say that the question that we want to answer is whether can neuromorphic onboard processing improve latency, autonomy, power consumption, and data volume across different spacecraft applications.
We're also going to investigate whether lower antenna power is necessary for detections because of the noise tolerance of both the hardware and software we're using. And then the application level KPI are we suspect because of that change in duty cycle, we could increase our imaging time and therefore coverage by at least a factor of 2. And the latency and timing end-to-end from imaging to detection to self-queuing is expected to improve with NeuroSAR from hours to minutes, or at least a factor of 5.